Yeah. Thank you, everyone. Thank you for joining in. So today we have Shuyu, and she'll be giving an introduction to representation learning, approaches, challenges, and application. So we welcome Shuyu, who is currently a PhD candidate in Department of Computer Science, University of Oxford. Please go ahead, Shuyu. Please go ahead.
Right. Thank you for the invitation. And yes, my PhD is about representation learning, which I believe is at the core of machine learning and AI research. So today I want to give you an introduction to this topic, and we will look at some definition of it because somehow I find it at the start of my research being a little bit abstract. It's kind of up to interpretation. Then we'll look at existing approaches to derive representations, and we'll look at some applications, how to use that. So yeah, I think I just mentioned about this overview. Then we can get started. So we are all AI researchers. So I believe we kind of think about problems sometimes or oftentimes from a philosophical perspective. What is representation learning, right? This is actually we can go very philosophical with this question. Then let's be more concrete. If we look at a picture, or look at this cat in particular, then what is a good representation of this cat? Well, the most simple kind of attempt would be saying, well, this is a cat. We can just use this cat as a representation of this image. Well, this works because it does summarize the million or megapixel of this image into a single word. So it does kind of like do something through this representation process. However, it has some limitation. For example, if I look at this image, I would be able to answer a question like, is this cat mine? Right? I can distinguish it. But then if I just look at this representation of this image without being able to see the image, I'm not able to say whether this cat is mine. And I'm not able to answer what this cat is doing now. I'm also not able to tell you whether this cat is safe. So this current representation summarizes the information, but it summarizes a little bit too much. So we lose the ability to use this representation for many possible tasks that we actually want to engage it with. Then what this kind of like a little exercise give us a taste of what kind of representation we probably want to derive from our data. We probably want this representation to be a bit more descriptive of the data, but we also want it to be like a summary so that we don't have to deal with tons of millions of numbers at the same time. So I would say representation is a summary of data, which kind of omit the unnecessary details, but at the same time, it preserves important context. And we have to remember when we want to deal with those data with our computer, then they don't see the image as the same way as we kind of visually see it. They see the image and data as numbers. They see this arrays of number as the input information, and the representation accordingly we will derive would also be array of numbers because our computer have to process it. So this is kind of like making it more abstract. Each dimension of this representation would contain some semantic meaning, but it is not really straightforward to tell in advance, okay, the first dimension encode the color of the cat, and the second dimension encode different features. It is like a number how computer understand and summarizes the input array of numbers. So I think it's like good to start to look at representation from how it kind of evolves from the traditional machine learning tasks. So at the beginning, we kind of have those data, and we just want to do specific tasks on them. So for example, a classic one, like it was kind of a challenging machine learning task for many years, would be just to classify an input image into certain labels. So we have cat and dog. We just want to do a binary classification on this. For many years, this is a very challenging task because remember, the computer see the input image as a array of numbers, and those numbers could be very high dimensional. It depends on the resolution of your camera. So many times this didn't work so well. So if we directly act on this image as input data and learn a classifier to give us the output of a binary label, then usually this classification doesn't perform very well. Then over time, we find a way to make it perform reasonably by abstract certain features from the input data. So this, with this process, like a specific concept that emerges is dimension reduction. We know the problem is there is too much redundant information in the input array. So we summarize the relevant pieces of information out and put it together into a set of features for our classifier to deal with. At this stage, the features are mostly handcrafted. So we say edges are important, then we kind of define the filter to derive edges from an input image. So with those handcrafted feature, our classifier can work okay, give us reasonable accuracy. But it still doesn't kind of like nail the task of the classification, because we can do it, but our algorithm does not do as well as we do. So then kind of like about 8 years ago, deep learning modules come. So what deep learning does, different from previous approach, is that it no longer works with a predefined set of filters or a predefined set of features. It learns those features from the data for your task. So it's kind of like whatever feature is good to improve the accuracy, then the model summarizes those features out. With such approach, we achieve very good accuracy. So it's like compatible with human, even many times outperform human. So we like achieve superhuman performance on specific task. But then we want to challenge ourselves, right, in research. Then we think this is just like for a specific task. Is it possible that we can derive features that is not only for a pre-subscribed task, but those features are generally useful for a wide range of tasks, even the tasks that we do not know when we are learning it. So this is the start of representation learning. It's we're learning a set of features. We don't even know what we want those features to be, and we don't even know what we want to use this feature for, but we know those features will be useful. And this is like kind of opening up like so many conversations of what properties we want those features to contain, and how well we can evaluate those features as. So this is like all research questions that we have with representation learning. Yeah, so this is the kind of center of representation learning. So as I said, like, because the feature that we want to derive with representation learning is not known kind of at the design time, we don't really have observations of those representation. So the only way to derive it is to know what is a good representation. So we can design objective functions that encourage those properties to emerge. So here are a list of features that I think a good representation should obtain. So firstly, we have to relate to the definition of representation. We want the representation to summarize our data. So usually a good representation would be lower dimension. It would contain, it will like remove the unnecessary details of our data in this representation. So our later task can just handle with simpler kind of data to make their decision. So this low dimensional usually is a prerequisite for the representation. And again, representation emerges with the purpose of using for a wide range of tasks. So your representation should be reusable, like different dimensions. You should see it to be important for many tasks. You don't want like your representation, like the first 10 dimension is assigned for the first task and the second 10 is for the second task. You want to like all the dimensions of your representation to be used for all your tasks.
So, show you one question. Do you want questions in the middle or at the end?
I'm okay with either. Yeah.
So when we reduce the dimension, is there any disadvantage, or does this representation limit its application because there is dimensionality reduction?
Not necessarily, because sometimes if I just have an array of a white wall, then you literally have a single number for the number of pixels you have in the image. But then you could just like simplify the entire thing into a single number. So it's really when you reduce the dimension, how do you maintain the same amount of information? So it's kind of like the redundancy exists by we represent the same thing always in the same format, like the number of pixels of your camera. But then the thing is like the information in your image is not kind of proportional to the number of pixels. So many times like the number of pixels is more than the different information in your image. So you can reduce it without loss of information.
Got it. Thank you. Please go ahead.
Yeah, so we would also want our representation to be smooth. This is to do with kind of like the way how data is organized in your latent space. So for example, here we kind of show like a representation of handwritten digits. We want like similar data like all zeros to occupy a nearby region in this latent space. So in this way, when you explore this region, then you are seeing the changes in your data smoothly appearing. So this kind of like shows your latent space is organized based on the similarity of your data. Then you can efficiently explore your space by visiting the similar data. So this would be a very preferable property when you use the latent space for search or for optimization. Then this days kind of like is a very hot topic of this disentanglement in the latent space. So we would want to organize different properties of your data in specific dimensions. Then you would know if I just change this dimension, I'm just adjusting a specific thing of my data. Say if I have the color, the fur color of the animal in the first dimension, then by just adjusting that dimension, I'm only changing this single feature. I'm not changing like the size of the animal or like the eye color of the animal and stuff. So we want to have like this organization so we can make the latent space more interactive. And the final thing, which I think is very interesting, and there probably should be more research on this, is how to design this hierarchical structure in the latent space. Because if we just like represent our data in a flat feature vector, then it's not really kind of the way we build our understanding on the concept of the world. We kind of like have all these operations of within cat. We have many sub concepts associated with cat. So how to like maintain a similar data structure in the representation is a very interesting topic, and we should explore more. Yes, so that's the representation we would like to derive and how to derive them. So my research is about this approach of generative models. So it's kind of like deriving the representation in a reverse way as we would think about it. So we have data And the representation is kind of like a summary of the data. But then the generative model kind of go the other way. So it's like we start with the representation, and we know each representation associated with a data sample. Then we would be able to, by say, generate different feature vectors of this representation. And we would be able to see, oh, what data sample this feature vector actually correspond to. So it's kind of like drawing sample in this representation space, latent space, a lower dimension space, and you want to see, okay, what is the data associated with this piece of representation, or sometimes we call it code. So you can see it as like a big database, each code corresponding to a sample, and you can draw different samples of the code, then you see the corresponding data. So there are a few kind of like popular approaches in this generative models. So I was talking to JC earlier, and he said he had a few works in GAN. So GAN has been very popular, and there are many works exploring its application. So the way GAN learn it is we have this generative model which can generate data, and they learn it with another discriminator by saying, okay, whether the generated data looks real or not. If it's real enough, then the discriminator should not be able to distinguish it from a set of real data. But if it's not real enough, then I can specify, oh, this is generated. So basically, you want to have your generation to generate data as real as possible, so that another discriminator will not be able to tell the difference between it and the real data. So this is one way to learn it. And another way to learn it is actually through reconstruction, because we want like the generation to be as similar as possible as your input data. Why don't we just learn this like one-to-one correspondence between them? And we just guarantee that there is literally no holes between every single code words, then we have like a very compact description of our data set. So this is the philosophy of learning of variational autoencoder. You start with your data, you through an encoder, or oftentimes it's called inference model, you encode it into a lower dimension code, and then you reconstruct your input data. And at the same time, you also have another stream of this generation, which can just generate from a latent distribution. So that is kind of ignoring the encoding bit. I could just like draw random samples, then I would be able to generate novel samples that is not even exist in my data set. So what is the difference of, say, variational autoencoder from normal autoencoders? I would say is kind of the probabilistic formulation of it. So what does this mean? So the normal autoencoder would encode your data into a feature vector and then decode it back. So it's just like operations on the numbers directly. But then the variational autoencoder takes a probabilistic interpolation of everything. So first, your data sample is actually like draw from a data distribution. So you believe your data lies in this distribution. Like this one is a oversimplification of the data. So apparently your data is like of the dimension of number of pixels. So it's a very high dimensional vector. But you would imagine there still exists a distribution in this high dimensional space. And if you draw a sample, so like in this kind of high dimensional distribution of my data, I draw a sample, then I would get a single image in this human face, say, data set. Then that's like my data distribution. You would also have a distribution for your latent code. So now you encode this data sample into your latent space. It's no longer just a feature vector. It's not just a single like 10-dimensional number. It's actually in a distribution in the latent space often we just use like a very narrow Gaussian to represent it, but then it's no longer a fixed vector. It could be like a vector slightly to the right, or it could be a feature vector slightly to the left. So the exact number, there is a little bit stochasticity in the feature vector to represent the specific data sample. So this add into the formulation, and their learning objective is all based on probability derivation. So this is the learning objective they use to learn the unknown parameters in the model. What are those unknown parameters? Is the parameters in your encoder and decoder models. So they learn under this objective to optimize it by changing the parameter values in your model. So we will go through like each term of it so that it doesn't look as scary as it is now. So
just one question. So this is fine when you have images and you reduce the dimensionality, but let's say we are considering single dimension data, just time series. So in that case, does anything change, or how would you tackle that problem?
So things actually generalize to different data type. So if we have image, which is say the number of pixel dimension, then you have like array of this dimension numbers. But then if it's time series, so I will show an example of anomaly detection later, then it would be the number of dimensions of say this current window you look at. So say I'm looking at a window of 100 samples as like one input data, then that would be it's a 100 dimension data number for this X.
100 cross 1. So 100
yeah, 100 by 1. But even if you just have a single dimension data, which is say just a number, then you can still use this formulation, because what you would believe is like in the single dimension, my data is kind of always lying, say, a certain range of this single, like basically this number. So my data is always between, say, 1.8 to 2.2. So it's always between this range. So I'm learning which range my data actually sit in. So it's kind of like, it doesn't matter what dimension your data is, you are learning what is the region your data actually sit in, basically.
Got it. Yeah, please continue.
Yeah. So this is like kind of looking scary equation, but then what it encodes is actually something very intuitive when we go through it step by step. So we read this equation by starting from the first expectation term. So in probability theory, expectation means we draw a sample from the distribution kind of at the bottom. So remember, this distribution PDX is actually just our data distribution for the data set. So by drawing one sample, we're simply just pulling out one image from, or one example from our data set. And we are looking at this specific example of our data. We wanted to estimate what is the latent code for this sample. So this conditional distribution literally tells us we want to know what is the latent representation of this data sample. So that is basically this encoding process. So we have one data sample draw from our data set, and we derive its latent code. And remember, this latent code is a distribution. So then we kind of get this distribution and we draw a sample from this distribution. Then we want to evaluate how likely a data sample actually would be generated using this representation. So this is the decoding process, the generation process. Given this latent code, what is the likelihood of I'm actually using the data from this generated image? So the first term together is just a single pass of the autoencoder. It's like we draw a sample from our data set and we generated it, and we evaluate how likely my data is actually generated with the corresponding latent code. So that's literally the first term, to compute the reconstruction error. And then the second term relates to the probability distribution of the representation. So our code is like kind of like this like narrow probability distribution. And we want this distribution to be as similar as possible to like usually like kind of a pre-Truson distribution, like a unit Gaussian. So you can think this as like a regularization. So it's saying in the vast latent space, which could be from -infinity to +infinity, where do I actually put my code at? It could be anywhere. So to just like give it a little bit structure, I want it to be close to like say zero code. I want all the embedding to be like remain close to this like center of the latent space. This is just to like kind of put it into a specific location in the infinity possible regions in the latent space. So the second term is just a regularization in our learning process in the latent code locations. So together with this tool, then we are able to learn the parameters in the model, in our autoencoder model, in the encoder and decoder. So with this, you have a method to derive the representations for your data. So now with this like representation learning method available, then we can use it for some task. I will demonstrate two tasks using the representation based on my research. So the first one we'll look at is anomaly detection in time series. And then the second one we'll look at something more just exploring the derived latent space. So just a little bit motivation in the anomaly detection. I actually believe we all probably can see it quite straightforward. But there are several examples. So for example, in the financial data, we would want to know when we want to sell and buy a stock. And for like kind of an industrial point of view, when you have like the data about how well your machine is doing, you want to know when a failure might appear, then you want to preempt this failure in advance. And for like healthcare, when we monitor the health status of a patient, we want to know when our patient is in critical condition and assist help like accordingly. So there are so many situations in our life that anomaly detection in time series is very important, and we want to do it well. However, this task is very difficult actually, and mainly for two reasons. The first one is like the label, the anomaly label is very rare. Like we don't often have experts sitting there to tell us, okay, there will be one anomaly appearing 100 days down your machine. And often like we don't really have very good definition of those anomalies. Like often you just have the anomalies when something dramatically failed, then you know, okay, that's a failure. So those labels are very difficult to acquire. Like in general, we would say anomaly detection is an unsupervised learning task, and we want to do it regardless of all these difficulties. So like some high-level sketches for the solution for anomaly detection task. So those like ideas are generalizable to most of anomaly detection algorithms. It's not specific for representation learning. So often what we want to do with anomaly detection is to summarize the normal behaviors really well. So say we have data and we believe anomaly is rare events, then we can assume like the existence of those anomalies can be almost like 0%. Then we just assume we have a dominantly normal data. Then we want to summarize what is the normal behavior really well. Then at test time, when we observe a new kind of data sample, say like a sequence of time series, like 1 day worth of data, then we just compare this 1 day data with all the normal data or normal behaviors we know of to decide whether it's similar enough to the normal behavior. If it is similar enough, then it is a normal behavior continued. If it's not similar enough, then it would be something very novel, either good or bad. So we just highlight it with a high suspicion. So this is the high-level idea for anomaly detection. If we directly apply, say, like our representation learning from VAE for this task, then what we would do is saying we have this like sliding window across our normal time series, like a long period of data. Then we're just sliding it through, and we're assuming most of it is normal. Then we just learn like a representation for those normal data, summarize all the normal behaviors in the latent space. Every one normal window of our time sequence would be summarized into a feature vector or like a small distribution in the latent space. And overall of them would be all the normal behaviors. So we just do this representation learning for normal data. Then at test time, we use the reconstruction error as like a anomaly detection metric to flag whether the new data sample is similar enough to our previously seen normal data. If the reconstruction error is high, that means we haven't seen such time sequence pattern in our training data. It has not been often observed as a normal behavior. Then it should be checked further. It should be considered as an anomaly. So this is like the direct application of representation learning. And this is like explored in this work that I put down here. Like a little bit sophisticated way to approach this task is to say we can look at the data at several different time window. So if we just learn the normal data for a local window, say 1 day, then you would only understand the normal behavior for this kind of resolution. You only understand what is the normal data look like for 1 day. But what if like the anomaly only appears over 1 week period? Then maybe every day it looks good enough. But then if you look at the trend for 1 week or 1 month, then you will observe some pattern that is abnormal. So this is where we propose in our recent work kind of earlier this year. So we learn the representations for short windows like 1 day through VAE to summarize that into a low dimension feature or embedding. Then on this embedding, we look at a longer period to summarize the patterns for the longer period of time. This will give us like the understanding of the normal behavior over much longer period. Yeah, so this will also slide across the training data. Then we consider the anomaly for the reconstructions of these 2 processes combined. So in the reconstruction, you consider the local window accuracy, whether at a local time resolution, whether the behavior is normal enough. And also you consider over a longer period based on whether I can predict the next window from the previous K-1 windows. Then we consider this like 2 resolutions of reconstruction error to decide whether there is an anomaly or not in our data. So by doing so, we are able to detect the anomaly pattern both in a shorter window and a long-term window. So this allows us the flexibility to detect anomalies for different time scales. So this is like one idea that we explored in recent work. There's some fancy highlighting timescale. So we show that using this way to do anomaly detection, we can achieve some very good performance for this task. So again, like I would say the anomaly detection, even though we have like in the research community, there has been like a very long time study and exploration in this topic, but there are so many questions still need to be answered. So for example, how to evaluate like a method on anomaly detection. With all the challenges of like very limited label data and stuff, it's very difficult. So usually I would say the best way to look at it is by this like qualitative inspection. So when you have a test sample and you just have like very sparsely, like say here we only have 2 incidents of the anomaly detection, then you just need to look where your method actually detect anomalies and see whether it's actually a sensible behavior. So for example, for this time sequence of machine temperature, from the label, we know there are 2 failures that the factory actually reported. Our anomaly detection is those green bars at the bottom. So we detect both of them, but then the first detection actually happens kind of after the anomaly incidence. So it only detected after it has already appeared, which is a little bit kind of unsatisfactory because you would already know it by that time. But then for the second anomaly detection, we detected ahead of time. So the method detects some abnormal pattern, which is building up to the time the factory report a fatal failure. So this would be very useful because then at this time you would already like start some action. You probably already put the production on hold before the failure actually occurs. The method also detects something which is in the middle. So there isn't like a positive anomaly label here, but then it probably is something very useful because this pattern is like strange enough that even though a fatal failure was not reported, but maybe the expert should go into there to check whether there is anything wrong there and building up. So this is very important for safety critical conditions. So comparing with, say, the like naive approach of anomaly detection using representation learning directly. So this would be the VAE approach for anomaly detection. So the anomaly detection label looks like this. So again, they also detected both anomaly incidents, but then the problem is they also flag so many positive, false positive alerts that it might be a little bit problematic for the factory because the expert has to go in every time there is an anomaly flag to check whether anything is wrong. When there are so many in your factory, then it becomes like less cost effective because the experts basically checking every single day. Then you want the false positive also remain low as possible.
Shuyu, there are a couple
Yep.
of questions. Antonio, can you please unmute yourself and go ahead with the question? Antonio?
Sure, thank you. I thought that this approach is really interesting to you. And I would like to ask you, how are the VAE models trained? Do you train the VAE-LSTM and the VAE small model for one day independently? And there's no correlation with the weights or anything?
Right, yes. So this is actually a very good question. And I think there are multiple ways to implement this. So for our learning, we explored one specific way. So we learn VAE independently on itself. So we learn the VAE as kind of like dimension reduction or feature representation for a local window first. So we have this time sequence, like in our training data, usually it's like 3 months of data, and we usually look at 1 day as a local window. So we just learn the representation for this 1 day window into this like low dimension embedding on its own first. And after deriving it, then we fix the VAE's weight. Just use the like learned embedding to train an LSTM on, say, usually we train it for a week worth of data. We just train it for the 1 window ahead prediction.
So you decided to use the encoders from the 1 day VAE to adapt for the VAE-LSTM architecture, right?
Yes, to train the LSTM, which only act on the latent feature vector, basically. So then at this time, after VAE is trained, then there is no kind of like raw data. We only act on the feature vectors.
And I see that this approach is more robust and and more complex. But have you tried just using two different VAEs, a 1-day period VAE and a larger one that uses a bigger scale, like a 1-week VAE with a different encoder?
Yes, so we kind of like decide the size of this local and long-term window, like, based on like our prior knowledge of what is a sensible choice. So say the machine data, we have it every 1 hour. So we think like 1 day is short enough to consider as a local window. Then we just take that kind of semantic meaning to decide the window size. And then we think like 1 week would be a kind of middle-sized window that we want to supervise anything is changing here in this scale. So we just take it as like based on like our a human understanding of what is a reasonable size of the period. But it is a hyperparameter that I think you should like validate. So based on different choices of the local window length and the long-term window length to see what is the best performance. Yes.
But I see. But it's just have you tried any approach without the LSTM with just two different VAEs with different scales, training independent?
Oh, so 2 different VAEs, then you would mean replace the LSTM with another VAE just on the latent embedding.
And maybe trying a type of multi-scale feature fusion for these two features from obtained for 2 different VAEs, a larger one and a smaller one.
Right. Yes. So I think I did some further analysis. So for the submission, I didn't explore that further. But then after this, I'm still like working on the extension of this work. So I tried, say, using VAEs for different scale, like basically your window kind of changes from 1 day to 7 days. So basically 1 day, 2 day, 3 day, up to 7 days. Then the performance kind of peaked when the VAE works like a shorter window. So it seems like VAE is very good at learning patterns of like less complex pattern, basically kind of summarize the shorter window into some basis pattern feature vector that represent certain basis patterns. When it's like longer enough, then you would have much more possibilities of different patterns. Then they start to not learn those patterns very well. The reconstruction start to like remain a high error. So I think
makes sense. Yeah.
Thank you. Yeah, thank you, Antonio. Maybe you can just introduce yourself so that Shuyu knows what you're working on, just to.
Oh, thank you. I'm a PhD student at the Pontifical Catholic University in Rio de Janeiro from Brazil. And I'm studying computer vision. I actually study semantic segmentation methods and object detection methods.
Right.
And I'm very interested in generative models. So I've studied a little bit of VAEs, but I stopped on the hierarchical VAEs. So it's another, and I didn't see any approach applying VAEs together with LSTM. So it's very interesting.
Right. Yes. Yeah. Thank you very much for the introduction. Yes, I'll also check out your work on the semantic segmentation. Yeah. So are you using VAE as well for this task?
No, not yet. I'm just use it with semantic segmentation models that basically use multi-scale convolutions for semantic segmentations. But I am very interested in getting to unsupervised learning, so I'm studying a little bit of VAEs, and maybe the hierarchical VAEs are the best option right now, because normal VAEs, simple VAEs, actually aren't even expected to work well, because they try to approach a super complex distribution to a simple Gaussian distribution. It's already like a lost game if you try to do this. So this hierarchical approaches might be the good methods to explore now. But there's also this VAE-LSTM combined with LSTM are very interesting. It's a very different idea that I haven't tried yet.
Yes, definitely. There are some recent work on the hierarchical design of VAEs. So they kind of like have layers of latent code.
Yeah,
yes,
maybe when you apply something like a hierarchical VAE with a bigger scale for your work, since you said that you tried as a bigger window for your experiments with one VAE, a VAE only. Maybe if you try to adapt a hierarchical VAE and compare, it would be very interesting to compare your simple VAE plus LSTM hybrid model with a hierarchical VAE with a bigger window, and see what would do better.
Yes.
Work to compare these two.
Yes, definitely.
Maybe the hierarchical representations could like outperform this VAE plus LSTM. I don't know. But
yes.
This is very interesting work here. Thank you. You can
continue.
Thank you, Antonia. Thank you very much. Shambhavi also has some similar question. Please go on, Shambhavi.
Hi, Lynn. I am fairly new to the scope of generative modeling. I had this question, like since we are operating with LSTM, which are more suitable for text data or like time series data, can we also combine some image-based models, say very easy, a ResNet with VAE to detect anomalies in images? Has such work been done in past? Can you refer to something?
So are you saying we will be learning a low-dimensional representation of images, and then we apply our STM on this representation space?
Right, like I had read about one specialized kind of GAN being used to detect tumors in medical images. So I'm referring to that.
Yes, I think that would be a very interesting approach to try actually. So it's kind of like treating the images, like this would be kind of like considering a video as your data, right? So you have a sequence of images, and then each image would be like a data sample, like say a window corresponding to this time sequence, and you summarize it into a low dimension feature vector. Then you look at several images as a time sequence using LSTM to predict the temporal correlation in this video, right? So that would be the approach.
Okay, understood. Thank you so much.
Thank you, Shuyu. Please go ahead. Yeah, please.
Right. Thank you for many interesting questions, actually. Yeah, so there are still follow-up works on this. And our discussion gave me some interesting ideas to try next then. So like what we've seen so far is kind of like the representation of a single data sample. And what actually we have with this representation approach can also give us like a distribution of the entire data set. So that gives us something about like what is shared in common in this group of data. Say we look at data set of human faces, then we would have like a representation for this single face. But then at the same time, if we look at all different faces in our data set and then take their feature vectors, then we would have like a description of the entire data set. And example of this would be like this. So basically every single, we embed like a image into the latent space, a 2D latent space. So we embed all the data in our data set. So this is actually a distribution from the handwritten digits. So then we get like a group distribution of all handwritten digits kind of in this 2D dimension as such. So this literally summarizes where all the handwritten digits reside in our latent space. And any space outside this distribution would be the non-data, non-handwritten digit images. So you kind of like summarize your data in one part of the latent space, and then you summarize all the non-data in the other part. So you get a data set summary. So here is kind of like one example of the handwritten digits, and we actually color it with the different class label. So you can see like this summarization actually correspond to the semantic label quite well. So like different digits actually cluster with the samples of the same class. So knowing this kind of group information in the latent space, in your feature space, is very helpful because you can use it for later task. So for example, we show here, we can actually use this data distribution to explore the latent space much better. So a common task for machine learning to explore the latent space is by interpolate it, traverse it between two data samples. So by going through this traversal, you would be able to see whether your latent space derived is smooth, how one sample is changing into another sample. So for example, here we consider like the traversal passes among 3 pairs of images. So say we start from a 7, we want to see how the 7 is gonna change into like 1, 5, and 6 in our latent space. So oftentimes this like traversal task is done by say a linear interpolation. So we find where the feature vector of 7 is in our latent space, and we find where the target image is in our latent space. And then we just like kind of draw a linear path between these two feature vectors, and then just equally divide the path, and then that will give us a traversal between the two samples. So the problem of this approach is that it kind of ignores like this concept of where your data actually reside in the latent space. So say these two samples along the path between 7 and 1 actually are like reside in like a space that is quite low probability. So you can see it kind of like trying to jump over a gap, but then because ignore there actually is a gap in the latent space, it just like land directly on the gap. So the same as like this sample as well. So it kind of ignores where the data actually reside in your latent space if you just do this interpolation task naively. So what we think is, with the knowledge of where the data actually is in the latent space, we can respect this geometry much better. We can traverse our latent space with the knowledge of where the data actually lies. So we only kind of land in the place that there is a high probability that this point in the latent space actually correspond to a realistic data sample. So the traversal path that we would approach would be something looking like this. So we'll have a path that only land on the possible regions of data. So this way, we kind of like focus on the spaces where data exists and then ignore the spaces where data actually does not. So the comparison of these two approaches would be like this. So the top row is the traversal path from our approach. You would say we have 7 going smoothly to 1, and all the sample generated along this path all look realistic, all look like real digits. Whereas if you do this linear interpolation, then you would also have 7 goes to 1, but then in the middle, when the data sample land on the kind of non-data region or low probability data region, then the data sample generated will look unrealistic. So you will have this like unsmooth morphism between your data samples. So we can also apply this to much complex data like human faces. Then you can see almost a similar behavior. So the top row is using the interpolation with the respect of the data distribution in latent space. Then you will have like a smooth transition from the start sample to the target sample, and all the sample generated along the path is realistic. Whereas if you go through the linear interpolation, you can see that it definitely land on like the low probability region, because in the middle, it generates a data that doesn't look like a real face. This is more severe in this example. So this is kind of like the most simple way for us to engage with this data distribution. But we really expect there can be many different ways of using this knowledge of where your data is actually sitting in the latent space in many applications, and we expect more like creativity in this aspect. So I want to kind of end my presentation like in more kind of a researchy side, like say the research questions still remain, say in VAE. So I would say, like many other machine learning approaches, like oftentimes the problem lies in what your learning objective suggests you. So here in VAE, the learning objects like contains two terms. One is the reconstruction error that you want to minimize. You want to reconstruct your input data as well as possible. But then at the same time, you also want to regularize the feature vector you derive, which is the representation for our data, to be at a known, like predefined region in the latent space very well. So it's like two kind of like sometimes contradicting objective. But sometimes when you do reconstruction well, you kind of have to like jump away from other encodings so that like you can do both data sample very well. So these two like objectives collide with each other, and how to balance these two like is the central question for VAE learning. So here we show one example that in our research we notice like when the two objectives actually contradict each other. So here we show the 2D embedding again on the MNIST digits, the handwritten digits. And each blob here would be one data sample of the handwritten digits. Because it's a distribution, so you actually occupy like a region instead of just being a single dot. So you can see some of the examples say this tool, it actually embeds two different digits, but then the two blobs start to merge into each other. That means in this encoding process, you lose the detail between these two data sample. In the latent space, it become very difficult to distinguish them anymore. Then when you decode it, you basically decode the same digit. You literally decode the same image. Then you start to lose the differences between your data sample. And this is a problem because then I see two different cats, but then after this encoding, they all become the same cat. So this is a very big problem with VAE, and it's a very big behavior between VAE and GAN. So I would say kind of like a lot of research is going on this question, how to improve the learning objective of VAE so that it balances this preservation of information at the same time, like a well-behaved latent space at the same time. So, so if you are interested in VAE research, probably this is the area you also want to explore and put in your novel proposal. So I think with that, that's everything I want to talk today about VAE. And thank you very much for listening.
Thank you, Shuyu. I thought this was a great presentation. Well, one of the clearest presentations in VAEs that I've seen.
Thank you.
I will follow you on Twitter.
Thank you very much, Antonio. That's a very... Thank you very much. Yes, like let's follow each other on Twitter and I'll check up your research as well. The same with JC and Shem. Thank you very much for inviting me.
After your talk from BMVC, this one was also amazing. That one also I enjoyed a lot.
Oh, thank you so much. Thank you.
Right. Yes, I guess we are pretty much done with it. I'll stop the recording.
Okay, thank you.